Every single time your phone buzzes with a notification or your cursor zips across the screen the instant you move your mouse, you're actually witnessing a tiny, lightning-fast event called an interrupt. They are truly the unsung heroes that make all of our modern gadgets feel so incredibly responsive. So let's dive in and see exactly how they pull it off.
So, let's imagine for a second that you're building a medical device, maybe a heart monitor. The data you're collecting has to be absolutely perfect, totally rhythmic, without a single misbeat. A dropped signal could literally be catastrophic. So that's the central challenge, right? How do you design a system that can juggle other tasks, like updating the screen, without ever missing a critical event?
Well, the first and maybe most obvious way you might try to solve this is with a method called polling. It's simple, for sure, but as we're about to see, it's also deeply, deeply flawed, especially when precision is everything.
And this slide right here just visualizes the problem perfectly. With polling, the poor processor is stuck in a frantic loop, constantly asking, is there data yet? No. How about now? No? It's always busy. But then, look what happens when it has to do some heavy processing. It gets distracted, and poof, a critical biomedical sample is completely missed. Gone. This is what leads to data loss and that inconsistent timing we call jitter. It's just messy.
Here's a great way to think about it. A polling CPU is like a really anxious chef who just can't stop opening the oven door to check on the bread. Every time they do it, heat escapes, it's a huge waste of energy, and by being so distracted, they might actually miss that perfect golden brown moment. It is just not an efficient way to run a kitchen or a processor.
Okay, so if polling is our inefficient, anxious chef, what's the solution? Well, this is where the simple elegance of the interrupt comes into play. It's a total game changer.
Let's go back to our chef, the smart chef, right? They use an oven timer. That's our interrupt. They set the timer and then they can go do other things, prep the salad, chop vegetables, maybe even just relax for a minute. They trust that when the bread is ready, the timer will interrupt them with a ding. A CPU works the exact same way. It can go into a low-power sleep mode or handle other, less urgent tasks, totally confident that it'll get an alert the moment something important happens.
And when you put the two side by side, the difference is just night and day. Polling keeps the CPU spinning its wheels, burning power and risking data loss. It's sloppy. Interrupts, on the other hand, free up the CPU, sip power, guarantee a response, and deliver that beautiful rhythmic precision we need for things like medical signals.
All right, so we get why interrupts are so much better, but how do they actually work, under the hood? Let's follow the entire journey from a physical event all the way to the processor taking action. Okay, before we walk through the steps, you need to know this one key term, the Interrupt Service Routine, or ISR for short. The easiest way to think about it is as a tiny, super specialized to-do list for a very specific event. When a button gets pressed, the CPU doesn't have to waste time figuring out what to do. It just instantly jumps to the button press ISR. It's an emergency action plan. So what happens is this incredibly fast 5-step dance. First, a physical event happens. Bam, a button is pressed. Then a controller checks its priority level. Next, and this is super important, the CPU automatically saves whatever it was doing. It's like putting a bookmark in its current task. Then it runs that special ISR code. And finally, once the ISR is finished, it picks up its bookmark, restores its previous work, and carries on as if nothing ever happened. It's completely seamless. Now, you might be wondering, okay, but how does the CPU know which emergency plan to run? That's where something called the vector table comes in. You can think of it as a digital address book for emergencies. For every single possible interrupt, a timer, a button, a system error, there's an entry in this table that points the CPU to the exact memory address of the correct ISR function. It's like a perfect map. Now, a modern device can have dozens, maybe even hundreds of different things all trying to trigger an interrupt at once. You absolutely need a manager to handle all that potential chaos. And in today's processors, that manager is called the Nested Vectored Interrupt Controller. The Nested Vectored Interrupt Controller, or NVIC for short, is the piece of hardware that acts as the ultimate traffic cop. It sits right in between all the peripherals, the timers, buttons, communication ports, and the main CPU core. Its job is to field all the requests, keep track of which ones are active, and serves them up to the CPU in a nice, orderly fashion. But its most important job, by far, is managing priority. And this is where it gets really clever. Look at this slide. You can see a low-priority task, IRQB, is just chugging along. But then, bam, a high-priority event, IRQA, comes in.
The NVIC allows that more important task to preempt or interrupt the less important one. Once that high-priority job is done, the lower priority task just picks up right where it left off. This nesting is what guarantees the most critical tasks always get the CPU's immediate attention.
So knowing how all this works is one thing, but actually designing software that uses interrupts effectively, that's a whole different ballgame. And there are some golden rules you absolutely positively have to follow.
And the number one undisputed golden rule is this: keep your interrupt service routines short and fast. This visual metaphor is just perfect. An ISR should be like a feather. It gets in, it sets a flag or reads a value, and it gets out. Fast. It should never, ever be an anchor. Things like complex math or long delays are what we call blocking operations, and if you put those inside an ISR, you'll bog down the entire system. And that golden rule helps you avoid some very common and very painful mistakes. Putting heavy calculations in an ISR is a classic rookie error. Another one is something called priority inversion, like accidentally giving a simple button a higher priority than a critical sensor reading. And a really nasty one is forgetting to clear the interrupt flag, which makes the ISR run over and over and over in an infinite loop, completely freezing your device.
But when you get it right, the result is just beautiful. This slide shows you the payoff. Look at that top line. That's a sampling loop that just drifts over time because of other processing delays. But the bottom line, driven by a perfect system timer interrupt, is perfectly rhythmic. It's deterministic. And that level of precision is exactly what's required for advanced medical analysis, like calculating heart rate variability.
So the next time you tap your screen or get a text, just remember there's this entire incredible ecosystem of interrupts, managers, and priority lists firing off behind the scenes. It all works flawlessly until it doesn't. And that leaves us with one final thought. We've seen how this system is designed for perfect order. But what happens when the chaos of too many requests overwhelms the manager? Well, that's when your perfectly responsive device suddenly isn't so responsive anymore.